The final portion of Chapter 6 that we discuss in this course is on wind. There is enough information that I need to divide this into two videos. The first video, we're going to discuss the two primary forces that drive the wind. So take a quick look. Why does wind blow? Well, let's look back at a principle you probably recall from a high school physics course. Newton's first law states that an object at rest will remain at rest, or an object in motion will remain in motion unless a force acts on the object. The same principle applies to air. The air will remain still unless there is a force to act on it. Well, it so turns out that there are actually four forces that cause the air to accelerate. In other words, four forces that drive the air, get it to start moving instead of remaining at rest. Those four primary forces are called the pressure gradient force, coriolis force, centripetal force, and friction. This video will cover the first two, pressure gradient force and coriolis force, and then the succeeding video will cover centripetal and friction. Start off with the pressure gradient force. First of all, what is the pressure gradient force? It is a difference in air pressure between two different points, such as in this figure we have two tanks of water. In the left tank there's more water, and since there's more weight, you're going to feel a higher pressure due to the larger amount of mass, the larger weight acting on the base. On the right, since there's less weight on that side, there's less pressure. Well, naturally things will start to flow from high pressure to low pressure. The larger the change in pressure, the faster this net force will be, the faster the flow will be. Also, the shorter the distance, the faster it will also be. So these are the 2 points in the second bullet. Large changes in pressure and short distances both yield strong pressure gradients and strong flow. And so we can quickly calculate the pressure gradient force or using the pressure gradient, which is calculated as the difference in pressure divided by the distance. I will not ask you to calculate these, but I do need you to know the relationship between the different components of this equation. For instance, if I took that water tank we saw on the previous slide and I increased the change in pressure, so it's a much larger difference in pressure, then what has to happen to the left side of my equation? It also has to increase. But if I leave the pressures alone and instead I increase the distance between those two pressures, then you're going to have the same change in pressure, but it has to flow over a larger distance. Therefore, your pressure gradient is smaller and you have a weaker force. All right. That being said, this is very important because the pressure gradient force is the initial force that causes the wind to blow. Without the pressure gradient force, the other three forces mean absolutely nothing. Okay, so what does the pressure gradient force look like? Well, let's take a high pressure on the left, low pressure on the right, and let's create a couple of contours for 1,020 millibars and 1,016 millibars. What would be that physical distance? 100 kilometers. Well, remember that our equation was that the pressure gradient is going to be our change in pressure, which is 4 millibars between these two cities, these two contours. It's a difference of 4 millibars. And down here on the map, it shows that distance is 100 kilometers. So your pressure gradient is 4 millibars per 100 kilometers. Now, what direction will the wind actually blow? Well, it'll go directly from high to low, and the important point from this picture, your contours are one direction, your wind is going to be completely perpendicular to those contours. Now here's another picture looking at a high pressure system with a few contours around. Now there are a few points I want you to notice. First of all, each isobar has a difference of 4 millibars. 1024 minus 4 would be 1020, minus another 4 is 1016. So we have the same pressure difference between each isobar. But I want you to look at the distance. Here on the left, notice the distance is relatively short compared to the distances on the right. So if I increase the distance, recall from a couple slides ago, if I increase the distance, the pressure gradient decreases and so does the force. Therefore, on the left, because it's a shorter distance, I get stronger winds because of a larger pressure gradient force. And on the right, because of a larger distance between isobars, I get a weaker pressure gradient force, therefore weaker winds. The second force we need to talk about is the Coriolis force. Coriolis force is not a real force in the sense of the word. It's not something that's actually pushing on something else. The Coriolis force is an apparent force that deflects objects because of the rotation of the Earth. Let's take this figure here. Let's say that you and a friend are on a merry-go-round, and you're just passing the ball to each other. And then some smart aleck, I don't know, me maybe, comes along and decides to turn you. Well, what happens to that ball? Well, the laws of physics say that that ball will continue to move in a straight line. But from your point of view, when you start here, you start the ball rolling away from you, but then you rotate away. So from your point of view, it looks as if the ball has rolled towards the other person and then turned. Did the ball really go a different direction? No. But it looks like that because your reference frame is changing. So the Earth is also rotating. We get a deflection here. In the northern hemisphere, things will be deflected towards the right, and in the southern hemisphere, things will be deflected to the left. Simple example would be we have an airplane. Let's say that you start off in, I don't know, San Diego, somewhere around here. And you decide to make a flight to Daytona Beach, pretty close to this line. So that would be your actual flight path. But in the time it takes you to make that flight, the Earth has rotated, so Daytona Beach has actually moved to another place. Now, what this would look like from an airplane's point of view, you start in San Diego, which was here at the time, but by the time you reach your destination, Daytona Beach, it has moved away. You find yourself, Yucatan Peninsula, somewhere down there. So because of the rotation of the Earth, your destination has moved, so it's an apparent change in your path. Couple other things to note here. If you were to start at some place on the equator and plan to move right along the equator, notice there would be no deviation at all. That's just one of the natures of the Earth's rotation. If you were to fly from point A to point B along the equator, point B would move away from you, but it would still be on the equator, and your flight would still be on the equator. It would just take you a little more time. Now, if you go closer to the poles, notice that the deviation is even larger than it was at 30 degrees latitude. So the closer to the poles, the larger the Coriolis effect is. The closer to the equator, the weaker the Coriolis effect is. Now, another important point about the Coriolis force is that it only influences the direction, not the speed. So, Coriolis force is greater as you get closer to the poles, weaker as you get closer to the equator, It influences the direction, not the speed. And finally, the coriolis force only has a significant impact over long distances. You can hear of demonstrations where if you're sitting near the equator, on one side you drain a bowl, it goes counterclockwise. Go to the other side, the water drains clockwise. This is a bogus demonstration. It's rigged because, first of all, this demonstration is too close to the equator and there is no Coriolis effect at the equator. And second of all, likely you're looking at a small basin, which is not a long distance. So these are rigged demonstrations. True, it shows true points of science, but it is still a rigged demo. Okay, so let's combine pressure gradient force and Coriolis force. So you have a high pressure. In this case, north is this direction on your map. So high pressure is on the south, low pressure is on up to the north. Pressure gradient force then points high to low. Therefore, your pressure gradient force initially kicks off your wind moving towards the north. But as the wind moves a little bit faster, the Coriolis force starts to kick in. The faster the wind moves, the stronger the Coriolis effect is, until you get to this point where the pressure gradient force and the Coriolis force are completely balanced. And at that point, the wind is going to be flowing perfectly parallel to the isobars. Now, how fast is this wind going to be? Again, that depends on the spacing of the isobars. Closer together means you have faster winds. Isobars that are more spread out mean you have slower winds. You can compare this to a river. When you have a river with wide banks, you have a nice, soft, easy flow. But if the banks get narrower, like they do here, then the flow is a lot faster, and this is the area where you would see whitewater rapids, turbulence, and it's not very steady or soft. Same thing with the wind. When the spacing is large, you're going to have a weak pressure gradient force, therefore you're going to have weak winds. But over here, if you have closer isobars, you're going to have a stronger pressure gradient force and stronger winds. Now, you can take a look at the current geostrophic winds. If you look on Falcon Online, there's my link to my Daytona State weather page. Not an official site, of course, just a page that I created for your use. You can go on there and you can actually see a figure that looks like this. That is the current geostrophic wind, the winds aloft for our current time frame. What you'll see is a colored figure. The stronger the color towards this pink, the faster the winds are. And the less color, the slower they are. What you see is winds are moving, sure enough, parallel to the lines. I'm not going very smoothly in my drawing, but forgive me there. The winds are moving parallel to the lines. This line I just traced out right here would be one of the edges of what we call the jet stream, just for reference. The important thing I want you to get from this figure is that the winds are blowing parallel to the isobars because of geostrophic winds. Okay, so that's it for this video. Those are the first two forces. In the next video, we're going to finish up our discussion on winds, talking about centripetal force and friction.